Greetings. Welcome to the 10th lesson in a series of lessons on basics of power systems engineering. There are two principal methods of analyzing electrical circuits. Those are the loop method and the node method. The loop method was discussed in lesson 9. This lesson covers the nodal method. Consider the circuit on this slide. Once the values of the elements of the circuit have been specified, circuit analysis allows calculation of currents in each branch of the circuit as well as voltages between any pair of points on this circuit. To apply the nodal method, we first determine all of the principal nodes of the circuit. Principal nodes are the nodes that have 3 or more branches attached to them. For this circuit, those nodes are these 4. We need to set aside one of these nodes as a reference node, and once that is done, we will assign unknown voltages in the form of index variables such as V1, V2, V3, etc. to the remaining principal nodes. This is shown on the next slide for the circuit. I have marked my choice of reference node with the ground symbol and a 0 showing that it is at 0 potential. The other nodes are arbitrarily numbered from 1 to 3 and assigned values of V1, V2, V3 voltages, seen here. The purpose of the nodal method, as applied to the circuit, is to determine these voltages with respect to the ground. The next step would be to assign currents I1, I2, etc. to each of the branches of the numbered nodes, one node at a time. These are temporary variables used in an intermediate step. The reference node does not get this treatment. You can see the assignment of index current variables to node 1 branch. Those are right here, I1, I2, I3. The order in which they are assigned or numbered and the direction for each does not really matter, but I typically take them to be outgoing currents from the node. I'll explain the rest of the steps with the circuit fully specified and in the process of completely analyzing the circuit. Here are the voltages and the voltages of the voltage sources and the ohmic values of each of the resistors. The next step in the process is to write the KVL multiple times, in this case 3 times, starting from the reference node, going to node 1, and returning back to the reference node, each time through a different branch attached to node 1. In other words, we go from here to node 1. First time we go around this path. Next time we go up again. Next time around this path through the branch with I2, and the last time we go, after going to node 1, we come down I3 and then return to node 0. I'll show those more clearly on the next slide. Here is our first loop going from node 0 to node 1 and back to node 0. This one leaves node 1 through the branch marked with I1 for this current. As I go around this loop, I'm going to write voltage rises on the left side of an equation and voltage drops on the right side of the equal sign and add them together. As an example, starting from node 0, going through node 1, I have a voltage rise of V1, so I'm going to write that on the left-hand side of an equal sign. Following this loop in this direction of counterclockwise, I'll go across the 4 ohm resistor, and that one represents a voltage drop of 4 times I1. So that one goes on the right-hand side. The next voltage I come across is a 50 volt voltage drop, so that also goes on the right hand side. And finally I'll go through V3 before reaching the reference node. And passing V3, V3 represents a voltage drop of this magnitude, so V3 goes on the right hand side. I'll show that on the next slide as printed out. You can see V1 equals 4 times I1 plus 50 plus V3. One more time. The voltage rises on the left side, the voltage drops on the right side of the equal sign. So going through V1, V1 represents a voltage rise, so it goes on the left. 4 times I1 represents a voltage drop, so that goes on the right hand side. There is another voltage drop of 50, that goes on the right hand side, and a voltage drop of V3. So that one also gets added to the quantities on the right hand side. The idea is to form this equation, an equation that will have in it only one of these three currents and as many of the unknown voltages that appear along the loop. For this first one, we have just the I1 as an unknown current, and the rest of them are the different voltages. Now we will go around a second loop, but this time after we go to node 1, we follow the path of I2 and back. And you see that here. Again, going through the equation for it on this slide, you can see that going from 0 to V1 and beyond, there is a voltage rise of V1, so that goes on the left. A voltage drop along the way of 2 times I2, and that goes on the right hand side, and another drop of V2 in reaching reference node, so that goes on the right hand side. Notice I don't go through the details of this branch. Once I get to V2, I'll go right away to the 0 reference node and write the voltage drop as V2 on the right hand side. And finally, the third and last loop under consideration for this node, and that one goes after going to V1, it follows the path of I3. And let's look at the equation. So we go a voltage rise of V1 on the left, followed by a voltage drop of 2 times I3, plus minus. And so 2 times I3 goes on the right hand side, another drop of 50 volts added on the right hand side, and going through V3 there is another voltage drop of this size of V3, and that gets added to the right hand side of the equation. Each of these equations here can be solved independently of the other two to find I1, I2, and I3 from each of them respectively in terms of the V1, V2, V3. Once we have calculated the currents in terms of the voltages, we'll write the KCL at node V1 and we'll substitute the corresponding values for I1, I2, I3 in this KCL equation. You can see this work on the next few slides. So from equation 1, I have calculated I1 in terms of the rest. I1 equals V1 minus 50 minus V3 over 4. In a similar way, I've calculated I2 from the second equation, and that's shown here, and I3 from the third equation, and that's shown here. Now I will write the KCL. I've written the KCL at this node, which is I1 plus I2 plus I3 equals 0. And the last step is to substitute for each of these from these equations. I1 from here, I2 from here, and I3 from here. and you see that done on this page. So this is our first equation in the voltages V1, V2, V3 that was obtained by working on node 1. Each of the other two nodes will also provide their own equations in the V's, V1, V2, V3. Then the three equations, once they're obtained, will be solved as a system of three linear equations in three unknowns, and that's how we get the values of V1, V2, and V3. I've made a note of the equation here on the side so that we have it when we come to use it. Now we move to V2 and assign the three currents in any order we like. Again, we go through the loop 3 times. The first time we jump from loop 0 to loop 2, to node 0 to node 2 and move in the direction of I1 and write the equation similar to how we did it for node 1. Again, the voltage rises go on the left side of the equality and the voltage drop on the right. So the first voltage that I come across is a voltage rise of V2, goes on the left. The next voltage is 2 times I1, and that's the voltage drop. So that one goes on the right hand side. And the last voltage I come across before returning to the reference node is V1, and that's a voltage drop as I go from this point to the reference point. So V1 is the voltage drop and goes on the right hand side. The next loop again starts from the reference node, jumps up to V2, but this time it goes in this direction and back. And you see that on the next slide. Again, let's write the equation. The voltage rise of V2 on the left, and the only other voltage I come across is a voltage drop of 80 times V2, plus or minus 80 times V2, which goes on the right hand side. The third loop, again from 0 to V2, and this time I can just go right back to 0. So the branch actually forms also the loop I'm interested in. Voltage rise of V2 on the left. Coming back down, there is a voltage drop of 1.5 times I3 that goes here, and another voltage drop of 50 volts that gets added to it on the right hand side. Same process of finding I1, I2, I3 from these three equations. I1 from here, I2 from this one, and I3 from the last one. Write the KCL at this node. I1 plus I2 plus I3 equals 0, and then we'll substitute for I1, for I2, and for I3 from those equations, and form our second equation in voltages. And I'm just going to make a note of that here. And then we'll move to node 3 or V3. Again, 3 loops for this one. First, assign the currents I1, I2, I3. And the first loop from 0 or from the reference node to V3, and from V3 in the direction of I1 all the way back to the reference point. And the equation, I'll go through it step by step. The first voltage I come across is the V3 itself, which is a voltage rise. The next voltage is a voltage rise again of 50 volts, so that also gets added on the left hand side. The next voltage is in the 4 ohm resistor, and that is a plus minus 4i1, and that's a drop, so I put it on the right hand side. And the last voltage is a drop of V1 as I come back to the reference voltage. And so V1 is a drop that gets added to the right hand side of this equation. Moving on to the next loop, starting from the reference to V3, that's the V3 voltage rise, and then coming back to the reference voltage, to the reference node, I have a voltage drop of I2 times 2, or 2 times I2. That goes on the right hand side. The third loop for this last node, node V3, starting from reference to V3, so that's a rise of V3, going up through the third current I3, through the branch with the I3, I have a rise of 50 volts, so that also gets added on the left hand side, and another a drop of plus minus 2 times I3. Because it's a drop, it goes on the right hand side, and another drop of V1 in coming back to the reference node. So V1 also goes on the right hand side. I1, I2, I3 are calculated from each one of these three. And again, we write the KCL for this node, which is the same equation, I1 plus I2 plus I3 equals 0. And the last step is just to substitute for each of these currents from the left-hand side, equations. And here is our third equation in voltages. And here they are all in one place. And I'll move those up here. In the next slide, you'll see the simplified versions of these. I've gotten rid of all the fractional terms and simplified as much as possible, and we get these as a simplified form of the three equations. Now, to solve these three equations in three unknowns, you could use a calculator or you could use the Excel sheet. If you are on an exam situation, you probably have only access to a calculator. Make sure you have a calculator with you that does matrices and or does multiple equations in multiple unknowns. I have used the Excel sheet, and to do that I have formed the matrix of the coefficients: 5, -2, -3, -120, 283, and 0 because this term is missing, -3, 0, and 5, and multiplying those by V1, V2, V3, multiplying that matrix by this vector should produce 150, 8,000, and -150. I inverted this matrix in Excel and multiplied the inverse matrix by this vector to get the vector representing V1, V2, and V3. And here are the answers on the next page. V1, V2, and V3. Notice that these are voltages. These voltages are all with respect to the ground. So V1 is this value with respect to this point. V2 is this value with respect to the same reference voltage or reference node, and same with V3. From these we can find any of the currents in any of the branches and any voltages between any pair of points that may be required. I'll find a couple of these before ending this presentation. So let's say that we are asked to find the current in the 80 ohm resistor as well as the voltage drop in the 4 ohm resistor, this one, and the current through it. The voltage across the 80 ohm resistor is going to simply be V2 because V2 is with respect to this node, and that is 29 or 49.28 with 4 significant digits, this number here, this second one. The current for this branch, I, will be simply that voltage, V2, divided by 80, and that gives me 0.6160 amps through the 80 ohm resistor. For the other one, for I prime, this current here, I'll write the KVL in this loop, and starting here, or starting, let's say here at V1, as I come down across or through this, around this loop in the clockwise direction, there is a voltage drop of V1 minus V3. I wrote that here. I write everything this time on the left hand side, and I write voltage drops as positive and voltage rises as negative. So V1 minus V3 is a voltage drop. I wrote it as is. The 50 volt I come across is a voltage rise, so I write it as negative 50. And the next voltage I come across is 4 times I prime, and that's also a voltage drop given the direction I've chosen for the current. So because it's a voltage drop, I give it a positive sign, plus 4 I prime equals 0. And now if we solve for I prime, well, first I substitute all of the numbers. V1, V2 from here, and solve for I prime. And I prime is going to be 0.0451 amperes. To find the voltage across the 4 ohm resistor, which will have this polarity, given the direction of the current, I simply multiply this current by 4, and that comes to 0.1803 volts here. 1803 volts. The circuit was solved here is the same one that was analyzed in lesson 9 with the use of loop analysis in that lesson. The answers are naturally the same, however, the approaches are quite different, as you can see. We have reached the end of lesson 9, excuse me. This is Fouad Albandi, founder and instructor of the educational group Own Your Destiny. If you enjoyed watching my channel, please click on the subscribe button. You can also visit my website at the link shown on this page, own-your-destiny.mylearnworlds.com. Thanks for watching this video, and I hope to see you in another one of my presentations.